Picture the ultimate tech espionage thriller. You've got the world's most powerful nations, the strictest technology embargo in, well, modern history, and this absolute unstoppable drive to build the most advanced artificial intelligence on the planet.
Yeah, it really does sound like a movie pitch, honestly.
Right. But it's exactly what's happening right now in the semiconductor industry. So today we are cracking open a massive stack of technical benchmarks, geopolitical think tank reports, and hardware spec sheets.
And we're trying to figure out how a Chinese AI lab called DeepSeek just pulled off the impossible.
Exactly. I mean, they managed to train a cutting-edge 1.6 trillion parameter AI model called V4 Pro. And the kicker, they did it using Huawei's Ascend 910C chips right in the teeth of crippling U.S. sanctions.
Yeah, looking at these reports from CSIS and the ITIF, it's just it's the classic scenario of an unstoppable force meeting an immovable object.
The immovable object being the trade restrictions, right?
Right. Restrictions designed to completely freeze China's access to advanced computing. And the unstoppable force is just the sheer economic and strategic momentum of AI development.
It's massive.
It is. And before we get into the actual silicon and the code, we really need to set the parameters for this analysis.
Oh, absolutely.
Because the source material involves intense geopolitical maneuvering, national security policies, and some really heavy international accusations regarding intellectual property.
Yeah, it's a minefield.
It is.
Yeah.
So our aim here is completely impartial. We are not taking sides. We are focusing purely on the mechanics, the facts, the hardware workarounds, and the economic data presented in the documents.
We're just analyzing this as a massive, undeniable shift in global technology architecture.
Exactly.
Because whether you are a developer building the next big AI app, or an investor analyzing the tech sector, or just someone fascinated by how technology shapes our reality, this bifurcation of the internet's brain will fundamentally change the tools you use and, well, how much they cost.
It's going to affect everyone.
Right. So to understand the scale of what DeepSeek and Huawei just pulled off, we have to look at the starting line. Back in 2019, the U.S. began imposing massive restrictions on Huawei and the Chinese semiconductor industry.
Yeah, and the main goal was to cut off their access to ASML's EUV lithography machines.
Which are basically the holy grail of chip manufacturing.
They really are. Those EUV, that stands for extreme ultraviolet machines, are the bottleneck of modern human progress. They are incredibly complex, highly restricted tools.
And they use light with a wavelength of just 13.5 nanometers, right?
Exactly. Just 13.5 nanometers to carve microscopic transistors into silicon. I mean, if you want to manufacture the world's most advanced microchips, like the 3-nanometer or 4-nanometer chips that power Western AI, you absolutely need EUV.
And the sanctions didn't stop there. They also cut off access to NVIDIA's top-tier AI chips.
Right, which are the unquestioned gold standard for training artificial intelligence.
Okay, let's unpack this.
Yeah.
Because that is a massive handicap.
It's huge.
It's like trying to build a championship-winning Formula One car, but you're legally banned from buying the best engine parts.
Yeah, and not just the parts.
Right. You're also banned from buying the precision tools required to actually make those engine parts yourself. So I'm looking at the timeline in our sources, and the obvious question just jumps out.
How do they do it?
Exactly. If Huawei and their manufacturing partner SMIC are cut off from extreme ultraviolet light, how are they physically carving chips small enough to even get on the track?
Well, they fell back on older technology, specifically DUV, or deep ultraviolet lithography.
Okay, DUV.
Yeah, and DUV uses a much wider wavelength of light, 193 nanometers.
Wait, 193? But they're trying to draw a 7-nanometer transistor.
Exactly. Try and draw a 7-nanometer transistor with a 193 nanometer light beam is just a physics nightmare.
I mean, that's like trying to paint a microscopic, hyper-realistic portrait using a thick, clumsy paint roller.
That is the perfect analogy.
But that shouldn't be physically possible. The paint would just bleed everywhere and completely ruin the circuit.
Yeah, it would. So to get around that physics problem, CIPIC employed a technique called multi-patterning.
Multi-patterning.
Right. Instead of using one clean flash of light to draw the circuit layer, like you would with an EUV machine, they run the exact same silicon wafer through the older DUV machines 3, 4, or even 5 times.
Wow. 5 times for one layer.
Yeah. They mask off different sections, drawing a little bit of the pattern, moving the mask, drawing a little more, basically overlapping the lines to artificially create tighter spacing.
Okay, I can see the catastrophic flaw in that immediately.
Oh,
I
yeah.
mean, if you are running a microscopic wafer through a machine 4 different times,
Right.
the alignment has to be flawless.
Absolutely flawless.
If layer 3 is off by literally a few atoms, the entire chip is garbage. The manufacturing yield,
Yeah.
the number of usable chips you actually get out of a batch, it must be terrible.
Oh, the yields are notoriously low, and the cost per chip is incredibly high because of all those ruined wafers.
Tossing out bad silicon all day.
Exactly. But what's fascinating here is how the academic papers and think tank analyses describe the broader outcome of these sanctions. They use a very specific term,
Which is?
a technological Streisand effect.
Oh, like when someone tries to legally suppress a photo on the internet, and the act of suppression just makes millions of people share it.
That's exactly it. The attempt to freeze their technological advancement forced a massive surge in domestic innovation.
So it backfired.
In a way, yes. Instead of stopping progress, the sanctions forced Huawei to look entirely inward. They had to optimize older equipment to its absolute theoretical limit.
Because they had no other choice.
Right. Necessity didn't just breed abstract ideas, it forced them to build highly specific, brute force hardware to overcome the literal physics of multi-patterning.
Which brings us to the actual physical chip they built to survive this embargo. Let's look under the hood of the Ascend 910C.
It's an interesting piece of hardware.
It is. The spec sheets show it's an evolution of their previous chip, the 910B. But since they are trapped on that older, highly inefficient 7-nanometer multi-pattern process, they can't just shrink the transistors.
Right, they can't just cram more processing power onto a single square of silicon like you normally would.
So their solution was a dual die design.
Yeah. And just for clarity, a die is simply the physical block of semiconducting material that contains the integrated circuit.
The brain of the chip.
Basically, yeah.
Yep.
Because they couldn't make one incredibly dense, highly advanced die, they manufactured two separate 7-nanometer dies and packaged them together on the exact same chip.
Forcing them to act as one unified brain.
Exactly.
It's the ultimate brute force workaround. Like, hey, we can't build a massive V12 engine, so let's just bolt two V6 engines together.
Yeah.
But the issue with bolting two engines together is the transmission, right? If those two silicon brains aren't communicating with zero latency, they'll just bottleneck each other.
And that transmission speed, the interconnect, is where the 910C actually shines. Yeah. The benchmark data shows it boasts about 3.2 terabytes per second of memory bandwidth.
Wow, 3.2 terabytes.
It's a massive data highway. It allows those two separate dies to rapidly share the massive datasets required for AI. And the raw output is significant too. The 910C hits around 800 TFLOPS in what's called FP16.
Okay, let me pause on FP16 for a second because I know that's crucial for understanding AI hardware.
It really is.
So FP16 stands for 16-bit floating point math. When an AI is learning, it doesn't need to calculate a number to, like, 50 decimal places, right?
Not at all.
It doesn't need to know the answer is exactly 10.0000001. It just needs to know the answer is roughly 10. And it needs to know it millions of times a second.
Right. FT16 trades hyper-precise decimal accuracy for sheer blistering speed.
And 800 trillion of those operations per second sounds massive.
It is massive. And there is a big but here when we look at the comparative benchmarks in our source stack, the reality check hits.
Okay, what's the reality check?
Even with the dual die setup and that massive bandwidth, the 910C is only comparable to about 80% of an NVIDIA H100 chip in raw capability.
Just 80%.
Yeah. And because it's running two older dies bolted together, its energy efficiency is notably worse. I mean, it draws a massive amount of power and generates a ton of heat.
See, I have to push back on the industry reaction here.
How so?
Well, I'm reading these tech publications, and everyone is treating the 910C like this monumental triumph. But an 80% success rate on speed and a worse track record on fuel efficiency isn't exactly a brag.
I see your point.
In a normal free market, this chip would be laughed out of the server room.
You're totally right. If Huawei had access to EUV machines and was still producing this, it would be a failure.
Right.
But we have to look at the context. In the context of a total global technology embargo, achieving 80% of an NVIDIA H100 using older DUV lithography and brute force packaging, that is a massive architectural achievement.
You're saying it shouldn't be physically possible.
It really shouldn't. But the hardware limitations do create a hard ceiling. To bridge that final 20% performance gap, You can't rely on the silicon anymore.
You have to rely on the code.
Exact.
Because a super powerful chip is really just an incredibly expensive, power-hungry space heater if you don't have the software to instruct it perfectly.
A very expensive space heater.
Which brings us to the software miracle that the AI lab DeepSeek pulled off. Let's talk about the preview of DeepSeek V4 Pro from April 2026.
The specs on this model are just staggering.
They really are. 1.6 trillion parameters. And parameters are essentially the digital synapses of the AI, right? The mathematical connections it forms to understand the world.
Yes, exactly.
And it has a 1 million token context window, meaning it can hold the equivalent of dozens of thick novels in its short-term memory during a single prompt.
It's massive, but the real headline in the technical documentation isn't just the size of the model.
What is it?
It's the fact that V4 Pro is the very first frontier-class model natively optimized for Huawei's Ascend hardware.
Oh.
Yeah. Specifically, they trained it on massive interconnected networks of these chips called Ascend 950 supernodes.
Natively trained.
Yes. Now, to be precise, the sources note that earlier variants of DeepSeek's models did rely heavily on stockpiles of pre-sanctioned NVIDIA H100 chips.
Sure, they used what they had left.
Right. But V4 Flash and the V4 Pro architectures were optimized directly on the Ascend hardware. They ran parallel verifications to ensure they could completely cut the cord from Western silicon.
And completely cutting the cord meant solving the synchronization nightmare. Because when you are training a 1.6 trillion parameter model, you aren't loading it onto one chip.
No, absolutely not.
You are slicing that massive digital brain across thousands of chips simultaneously.
And that introduces the gradient synchronization bottleneck.
Right.
See, during training, the AI processes a batch of data, updates its understanding, which we call a gradient, and then every single chip in the cluster has to share that updated homework with every other chip before they can take the next step.
I was reading about this networking challenge, and it's insane. It's like assigning a massive research paper to 10,000 students, and they're all working in a single Google Doc.
Oh, that sounds like a nightmare.
Right. If they all try to type at the exact same millisecond, the document just crashes. If one student's internet connection lags, all 9,999 other students have to sit there frozen, waiting for that one packet of data to arrive.
That's exactly how the cluster works.
So how did Huawei and DeepSeek bypass that traffic jam on older hardware?
They completely overhauled the networking architecture. Huawei historically struggled to network more than 124 cards without catastrophic data traffic jams.
So they had to fix the traffic flow.
Right. The reports detail how they utilized dedicated high-speed networking switches and custom ring topologies.
Ring topologies?
Yeah, essentially organizing the data flow into highly disciplined circles rather than a chaotic web. That let them scale smoothly across thousands of social nodes. But the networking hardware was only half the battle. The software translation layer is where DeepSeek really flexed its engineering muscle.
Ah, you're talking about CAN, C-A-N-N.
Yes.
This is Huawei's alternative to NVIDIA's U2. And for you listening, CDA is the entrenched software ecosystem that essentially translates human code into the specific math the NVIDIA GPU understands.
Right. It is the universal language of AI development.
It's the water the fish swim in.
Exactly.
So if CDA is the universal language, CAN is a completely different, highly complex dialect. How do you force your developers to abandon years of CD experience and rewrite the dictionary for CAN without losing years of development time?
Well, you don't rewrite the dictionary from scratch. You alter the compiler.
Oh, interesting.
Yeah. DeepSeek and Huawei engineers worked in an incredibly tight feedback loop to modify the backend of PyTorch. And PyTorch is the main framework developers use to write AI code.
Right. Everyone uses PyTorch.
So they built automated routing systems. That way, when a developer wrote standard PyTorch code, it seamlessly compiled into CAN instructions instead of CDA instructions.
But automated translation is notoriously inefficient.
It can be.
I mean, it's like running Shakespeare through Google Translate to Mandarin and then back to English.
Right.
You lose all the nuance.
That's a fair point.
And the hardware is already operating at an 80% handicap. If the software translation is sluggish, the whole system grinds to a halt. The third-party benchmarks must show a massive drop in efficiency, right?
Well, the benchmarks actually defy that assumption entirely.
Wait, really?
Yeah. The V4 Pro model scores a 93.5 on LiveCodeBench. It matches up directly against top models trained on premium NVIDIA hardware in rigorous evaluations like Codeforces and MMLU Pro.
That's incredible.
It is. The automated translation handled the bulk of the work. But to bridge that final efficiency gap, DeepSeek engineers performed manual kernel optimizations.
Okay, let's unpack manual kernel optimizations,
Hmm.
because this is where the sheer human willpower comes into play.
Oh, absolutely.
Because a kernel in GPU programming is the absolute lowest level foundational mathematical instruction. Normally, you let the compiler software write those instructions automatically to save time.
Right, but automated compilers aren't perfect. They leave tiny inefficiencies. So DeepSeek deployed human engineers to manually hand-code the mathematical operations at the assembly level.
Just writing the raw math.
Yes, they bypass the automated systems to squeeze every last microsecond of performance out of the Ascend architecture. It is painstakingly slow, agonizingly complex labor.
They literally had engineers going in with digital tweezers to hand-tune the math.
That's exactly what they did. And that excruciating human labor paid off in the inference data.
Inference being when the AI is actually running live, right?
Right, answering questions for a user in the real world. Through those manual kernel optimizations, DeepSeek achieves roughly 60% of an NVIDIA H100's performance in inference.
And here's where it gets really interesting, because all of that agonizing optimization on older, brute-forced hardware led to a jaw-dropping economic statistic in the source material.
It's my favorite data point in the whole stack.
By running this model natively on the Ascend hardware, DeepSeek achieved up to a 97% reduction in inference costs compared to previous pipelines.
97%.
Let me repeat that. A 97% drop in the cost of running the AI.
That single data point is an absolute earthquake for the tech industry.
I can imagine.
Because we talk a lot about the cost of training an AI, which, can run into the hundreds of millions of dollars. But training happens once. Inference happens billions of times a day.
Every time someone uses the app.
Right. If you are running an AI service for millions of everyday users, inference cost is your biggest ongoing existential expense. Dropping that cost by 97% completely rewrites the unit economics of artificial intelligence.
I imagine every single tech giant in China saw that profit margin and immediately wanted to switch their infrastructure.
Oh, the market data confirms exactly that. Companies like Alibaba, ByteDance, and Tencent saw the raw performance of V4 Pro and those incredible cost reductions, and they instantly pivoted.
They just jumped ship.
Yeah. They ordered hundreds of thousands of Ascend 950 chips. This sudden massive surge in domestic demand actually drove the physical price of Huawei's chips up by 20%.
Wow.
So the sanctions inadvertently created a booming, incredibly lucrative domestic market that Huawei now basically monopolizes.
So if we connect this to the bigger picture, we are watching a complete split happen in real time.
We are.
The initial sanctions intended to stifle development, but instead, they forced the creation of a completely parallel track. And now the geopolitical fallout is escalating again.
Yep, the U.S. is extending its restrictions.
Right, they're trying to limit the global use of these Ascend chips, not just their use inside China. That's creating massive diplomatic tension and completely fracturing global supply chains.
And this raises an important question about the future of global technology standards.
Oh, so?
Well, for the last 30 years, the world has largely operated on a unified tech stack. Whether a developer was in Berlin, Silicon Valley, or Shenzhen, they were using the same fundamental hardware protocols and software languages.
It was all compatible.
Exactly. This bifurcation threatens to end that era of interoperability. We are looking at a Western ecosystem completely dominated by premium, highly expensive NVIDIA hardware and the entrenched CUD stack.
And on the other side,
An emerging Chinese ecosystem prioritizing open-weight models and cheaper alternative hardware infrastructure.
so what does this all mean for you listening? For developers and international companies, this is a massive double-edged sword.
It really is.
On one hand, an emerging ecosystem means fresh opportunities. If you're a startup operating in a developing market, a 97% cost reduction in inference is literally the difference between launching your product and going completely bankrupt.
Right. Cheaper infrastructure democratizes who gets to build AI apps.
But on the flip side, it brings the absolute headache of fragmented global standards. We are rapidly entering a world where you might have to build your application twice, once for the Western AI ecosystem, and entirely from scratch for the Eastern one.
Yeah. The friction of conducting global business and, sharing scientific research globally is about to increase exponentially.
It's going to be a mess.
It is, but it's also important to note from the technical reports that this alternative ecosystem is not without its own massive hurdles.
They still have problems to solve.
Big ones. The DUV multi-patterning process we discussed earlier still plagues them with systemic manufacturing yield issues.
Still throwing away a lot of silicon.
Exactly. And the dual die packaging creates intense energy consumption problems. Not to mention the logistical nightmare of scaling these customized superclusters to millions of chips while avoiding hardware failures. Well, that remains an incredibly vulnerable bottleneck for Huawei.
So let's tie all of these threads together. The saga of DeepSeek and the Ascend 910C isn't just a dry technical brief about surviving a trade embargo.
No, it's much more than that.
By building a 1.6 trillion parameter model on severely restricted hardware, they prove that intense software optimization, literally hand-coding the math at the kernel level, can bypass almost any physical silicon roadblock,
Necessity forced a brute force hardware workaround.
which in turn forced a software miracle.
Exactly. And from a purely analytical standpoint, stripping away the ongoing political debates and the intellectual property disputes, the data in this deep dive is completely clear.
What's the bottom line?
The global chip war did not freeze AI development. It undeniably accelerated it, but it fractured the foundation, forcing human ingenuity onto unexpected, entirely isolated tracks.
Isolated tracks. And that brings us right back to the tech espionage thriller we started with.
It really does.
The blockade didn't stop the AI race, it just split the highway in two, which leaves us with a massive lingering question to mull over.
Let's hear it.
We're hurtling toward a reality with two completely separate digital infrastructures. If these two ecosystems completely stop talking to each other, and they train their highly advanced AIs on completely different hardware, different software languages, and fundamentally different sets of cultural data,
Yeah.
what happens when we eventually need those two AIs to communicate with each other?
Now, that is the trillion-parameter question for the next decade of computer science.
Something to keep in mind as you watch this incredible space evolve. Look closely at the hardware bottlenecks hiding behind the software miracles. Keep questioning your assumptions. And thank you for joining us on this deep dive.